Everyone expects I to the I to be imaginary, but it's not. It collapses into a real and tiny number, 0.2078. But I to the square root of 2 doesn't shrink at all. It just spins around the unit circle. One shrinks, one spins. Which one breaks your intuition more? So why does one shrink and the other just spin? To answer that, we have to change how we think about I. Instead of seeing I as just the square root of -1, we're going to treat it as a rotation on the complex plane. Let's go back to the real number line and build that idea from scratch. On the real number line, rotating 1 by 180 degrees is easy. We just multiply by -1, and the point jumps from 1 to -1. That's a flip. But what if I want a 90-degree rotation? No real number can take 1 and turn it exactly 90 degrees off the line. So let's invent a new move. I'll create a 90-degree rotation operator and call it R. Start at 1, apply R, and we rotate 90 degrees up to this new point. R. Apply R again, another 90 degrees, and we land at -1. That means R squared equals -1. So R behaves like a square root of -1. This mysterious rotation operator is exactly what mathematicians call I. From now on, we'll rename R as I, and think of I as rotate by 90 degrees on the complex plane. Now that I is our 90-degree rotation operator, let's tackle I to the I. On the complex plane, I lies on the unit circle at a 90-degree angle. That means it has magnitude 1 and angle pi over 2. In polar form, we can write I equals e to the power I times pi over 2. So the natural log, I equals I times pi over 2. Next comes the key power rule. For real numbers, you may have seen that x to the power a equals e to the power a times natural log of x for x greater than 0. Now apply it to I to the I. I to the I equals e to the power I times natural log I. We already found that natural log I equals I times pi over 2. So I to the I equals e to the power I multiplied by I times pi over 2, which simplifies to e to the power negative pi over 2. Numerically, that's about 0.21. So our 90-degree rotation operator raised to the power I turns into a real tiny number on the number line, a pure shrink by e to the minus pi over 2, with no rotation at all. Now, let's look at our second strange power. I to the square root of 2. We use the same power rule. I to the square root of 2 equals e to the power square root of 2 times the natural log of I. From before, we know the natural log of I equals I times pi over 2, so this becomes e to the power square root of 2 times I times pi over 2, which we can rewrite as e to the power I times pi over square root of 2. Euler's formula says e to the I times theta equals cosine theta plus I sine theta. So we got cosine of pi over square root of 2 plus I times sine of pi over square root of 2. That's a point on the unit circle at about 127 degrees up in the second quadrant. So raising our 90-degree rotation operator I to the real power square root of 2 is like doing a fractional number of quarter turns and landing at this strange, irrational angle. Now, put the two side by side. First, I to the I equals e to the power negative pi over 2, which is about 0.21. Imaginary base, imaginary exponent, but the answer is a real number on the number line, a tiny shrink. Second, I to the square root of 2 equals e to the power I times pi over square root of 2. A point on the unit circle with magnitude 1 and an irrational angle of about 127 degrees. This one is a pure spin, no shrinking or stretching, just rotation. Same base I, two different types of exponents. One collapses onto the real line, the other keeps spinning around the circle. If you like this kind of impossible math that actually has a clean visual explanation, hit like, subscribe, and tell me in the comments